Okay, welcome back. So we're working with this summation formula. 5.3, we're going to finally define the summation formula as a Riemann sum, which we'll use and sort of, I don't know, manipulate further on, later on in applications to do our bidding, essentially. If you can sort of open up the hood of the integral and go in there and play around with it, it turns out to be a good thing. But anyways, 5.3 Riemann sum and the definite integral. So first we kind of begin by generalizing our previous work on these summations, these sums of rectangles of areas for approximating area underneath the curve, right? So definition. Now in our definitions, we only require f of x to be defined. To formulate this sum. And then secondly, the subintervals don't have to be a constant change in x. Okay? Subintervals don't have to be equal widths. Change in x. In other words, change in x does not have to equal b minus a over n. Right? So if we have a function defined, what we're going to do is introduce kind of a new subinterval, and then we'll call the resulting sum Riemann sum. Okay, so we're letting f be defined on some interval from a to b, and we introduce this thing delta called a partition of a comma b, which is basically just a way of chopping up the interval over top which we have this area that we're trying to approximate. So delta is this partition of a to b given by whatever. So x sub 0 less than x sub 1 less than x sub 2 less than dot 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 less than x sub n, which equals b, where now the intervals are not necessarily like this, right? So where x sub I minus x sub I minus 1 is going to be change in x, we'll call it sub I, because now it's dependent, the width of those intervals is dependent on which interval you're dealing with. Okay, so given any particular point in that interval, so given a c sub I in the interval from x sub I minus 1 to x sub I, then we call this thing, we have, in other words, this thing, which is f of c sub I times change in x sub I from I equals 1 to n. We're going to call this thing in general the Riemann sum. Okay, so other things to note about this, and in order to pull off these limits now, we're not necessarily just letting the number of rectangles go to infinity. And instead, we're taking the largest interval and letting that go to 0. So note then we have this extra symbol, this magnitude of the partition, the norm of the partition, which is going to be defined as the width of the largest subinterval. Or the norm. And this thing is related to the old version of our change in x via the following formula, b minus a all over n is going to be less than or equal to this norm. Okay? And if you then divide both sides by the, if we multiply both sides by n and divide both sides by the norm, we have this relationship, b minus a all over the norm is less than or equal to n, which means now in our limits, instead of letting n go to infinity, we're going to let this norm go to 0. Okay? And that'll force n to go to infinity, which means when the norm goes to 0, then n will be forced to go to infinity. So in the book, the notation for the limits of these sums is we're going to use that norm in the definitions. So you'll see it like this: the limit as the norm goes to 0 of the sum of the Riemann sum But generally, when we're working the exercises, we'll drop this idea and just work with the limit as n goes to infinity, which is implied by this limit. Okay, so as the norm goes to 0, it forces n to go to infinity anyways. Okay, so we can write in this statement automatically and not really have to work with this norm issue. I believe that's the gist of what they're trying to get at. But anyways, let's look at example 1. So example 1 is interesting because instead of using our change in x equals b minus a over n, our change in x is this other formula. Okay, so what are we doing? We're given f of x equals change in x, and we want to evaluate the limit as n goes to infinity of the sum from I equals 1 to n of f of c sub I times change in x sub I, where c sub I will equal I squared all over n squared. And we want to use right endpoints on this thing. Okay. So what does the picture look like then? We have this square root function. Okay, my pen is dying on me. Let's see if this guy works. Yeah, we have a square root function. Let's call this 1, and this will be 1, so it's going up like this. And then these endpoints are getting progressively. So for example, if we have n equals 4, then c sub 1 will be 1 all over 16. And another pen just died. C sub 2 will equal 2 all over 16, which is 1/4. C sub 3 will equal 3 over 16, or rather 9 over 16, it's n squared. So this would be 4 over 16, sorry. This would be 9 over 16, and then C sub 4 would be 1. In other words, the rectangles over here are getting actually are having bigger and bigger widths, right? So C4 is at 1. Let's see where C1 is at 1/16. This is 1/4. So if this is 1, I could split it in half, and then here's 1/4 way over here. 1/16 would be like in here somewhere, and then at 1/4 I would have, and I'm using right hand endpoints for my rectangles, I'd have this rectangle, and then 9/16. So 8/16 would be 1/2. 9/16 is a little more than 1/2, right? So it'd be right here. And then the final rectangle would be right here. In other words, the delta x is not constant, is what we're getting at, right? So what the heck is the delta x in this case? So we note delta x sub I, that must equal the difference between two consecutive endpoints. So we will say, consider I squared all over n squared minus the one before it, which would be I minus 1 squared all over n squared. And so what do we have then? We have I squared minus I squared minus 2i, but then I distribute, so it'd be plus 2i, and then minus 1 all over n squared. So 2i minus 1 over n squared, okay, for our delta x sub I. Okay, then we're going to be able to figure out the area underneath this curve. So hence, we consider then the limit of the sum of f of, and we're using right-hand endpoints, so it's starting at 0 and then plus I squared over n squared, and then times delta x sub I, which is 2i minus 1 all over n squared. Okay, now we're going from I equals 1 to n and taking the limit as n goes to infinity, right, which is the result of assuming that we're taking the limit of the partitions going to 0. All right, so let's go ahead and figure this out. F of that expression, so the limit of the sum f of this, so I'm plugging this formula into this formula and taking the square root, I just get I over n, which is nice. Then times 2i minus 1 over n squared. Go ahead and multiply that out, so you get the limit of the sum of 2i squared minus I all over n cubed. Okay. And then we get the limit, and this pen is dying, the limit of the sum, and I'm going to butterfly this sum, so I end up with 2i squared over n cubed minus I all over n cubed, and then I'm going to split that sum into two parts, so I get the limit, and I'm going to factor out anything that's not dependent on I. So the limit of 2 all over n squared times the sum of I squared minus 1 all over n cubed times the sum of I. This thing then will have the limit of 2 over n squared times the sum of I squared, which is going to be, obviously, I lost something. Is this up here, n times n squared is n cubed. So this would be n cubed. I got it right there, but I missed it here. So this is an n cubed. So 2 over n cubed times n times n plus 1 times 2n plus 1 all over 6. Then minus 1 all over n cubed times the sum of this, which is just n times n plus 1 all over 2. Okay. So the limit of this thing, the numerator is 4n cubed, the denominator leading term is 6n cubed. So 4, 6, 2/3. This thing will be 0, and that'll be our answer. Okie dokie. So a little bit more complicated. Now we want to define this thing called the definite integral. And in other books, they kind of want, there's a requirement of continuity. So it's not a bad idea if you're super interested in this topic to kind of shop around a little bit, look at some of the other books and how they derive this. This book doesn't have the best exploration. I'm doing the best I can here with it, but section 2, the definite integral then. If we just have that f is defined on this interval from a to b, and we can actually figure out this limit. So the limit as the norm goes to 0 of the Riemann sum, if this thing exists, then we say its limit is the definite integral from a to b. Okay, so so if this thing exists, then the limit is this following object, which should look kind of familiar from chapter 5.1, sort of. Okay, so from 5.1, we labeled this as the antiderivative, the general antiderivative, or the indefinite integral. Now we have a definite integral, and what we do is put this a and b on it to let us know. So this is called the definite integral from a to b. Where a is the lower limit and b is the upper limit. And then kind of the part that's usually put in books, f is integrable so long as f is continuous. And then obviously later on you learn so long as f has a finite number of discontinuities, you can go ahead and integrate it. So anyways, let's look at it another example. So we have number 4 in the book. They want us to find the definite integral from -2 to the 3 of x dx. Okay. So the only way we have of doing this as of this point is the limit of the sum, and you can use right-hand endpoints, left-hand endpoints. You can use the delta x equals b minus a all over n in order to pull this off. What is this integral from -2 to 3? 1, 2, 1, 2, 3. It's the area underneath this curve, supposedly, here. But there's kind of an issue that we've not talked about, and that's this guy over here. You know, because it's going below the x-axis, if you were to think about the rectangles, the functional values of these rectangles when they're in this orientation, when they're kind of upside down, they're going to have negative areas, I think, right? So the sum probably won't be than the area underneath the curve, quote unquote. So what is this thing then equal to? Maybe is the question. Is it actually equal to 1/2 base times height? So 1/2 base here is 2, and then the height is 2, plus 1/2 base times height of the other guy. So the base was 3 and the height is 3. So 2 plus 9/2, so 13/2. We wish, right? So is this thing really just equal to 13/2? We can figure this out using, you know, I'm going to use my delta x equaling b minus a. So in this case, b minus a is 5/2, and I'm going to use right-hand endpoints. Right. In my Riemann sums, so this will be the limit, and I'll go directly to n going to infinity. I'll skip the whole partition baloney, of the sum of f of, and we start at -2, and then we're adding in 5 halves I, so 5I all over 2, and then again, the delta x is 5 halves. Okay. The function is just x. Okay, so when I plug this into here, I'll just get this right back out. So we'll have the limit of the sum of -2 plus 5I over 2 times 5 halves. And then that'll equal, this, what does this equal? Just for, I'm trying to say paper here now. So this is -5 plus 25I over 4. Okay. Or rather, yeah. Whoops, this should be n right here. Sorry, guys. These are n's. So delta x is 3 minus -2 over n. Sorry about that. Okay, so let's try that again then. What are we dealing with? I have the limit of the sum of -10 over n plus 25I over n squared. Okay. I can factor out anything that's not dependent on I, so you end up with the limit of -10 all over n times the sum of I, or sum of 1, sorry, and then plus 25 all over n squared times the sum of I. Okay, so that'll be the limit of -10 over n times n, which will be -10, and then plus 25 over n squared times n plus 1 over 2. So you get 25n squared over 2n squared, so 25 halves is the answer there. And then the limit of constant is just a constant, so we're getting -20 halves plus 25 halves, and certainly that's not equal to 13 halves, right? So what happened? What was the issue? Well, it's just what I said it was. When you're adding up these rectangles, they'll actually be negative. So you're getting negative area over here plus positive. So in particular, on the left-hand side of 0, you would have -2 plus 9 halves, which of course is -4 halves plus 9 halves, which of course then is the 5 halves that we got. Okay, so you'll see in definitions or theorems, for example, 5.5, you have to have that requirement of non-negativity for area. Okay, so theorem 5.5, if f is continuous and then non-negative, then you can automatically say that the area underneath the curve from A to B is equal to this definite integral from A to B of f of x dx. Okay. You can always sort of backpedal to the world of geometry when you're in a fix, and it's quite useful. In particular, here's number 33, where we have the integral from -1 to 1 of 1 minus absolute value of x dx. And what you're doing is just finding the area underneath this curve from -1 to 1. So you can use geometry. What is this thing? So absolute value of x is this. Negative absolute value of x is rotated. And then we're moving it up 1. So it'll be this guy. At -1, it's 0. At +1, it's 0. So I'm just trying to find the area of that triangle. So 1/2, this will equal 1/2 base times height. The base is 1, 2, and then the height is 1. So that integral should equal 1. That definite integral should equal 1. Here's one that is more hardcore. And what the heck is that thing? Well, this curve here, if if you think about it, y equals the square root of r squared minus x squared. That's the upper hemisphere of a circle, and we're integrating from negative r to r. So this guy right here is this upper hemisphere of a circle. Going from negative r to r is basically, we're trying to find this area. In other words, half the area of a circle. So it's 1/2 times pi r squared. In the end, the book's going to give you a bunch of basic properties of integrals, which you can kind of intuitively think about. So 4 properties of integrals. So firstly, the integral from a to a of f of x dx. You can kind of think of that as the area underneath the curve from a to a. What's the area underneath just a point? You know, what's the area underneath this thing? And you could probably guess 0. Okay. Secondly, then, if you're integrating from a to b, and then somebody walks in and flips your integral upside down from b to a, what's the relationship between these two integrals? Well, this guy is just going to be the negative of this guy. You could split up integrals just like we were able to split up derivatives. So the integral from a to b of f of x dx. Well, I guess this isn't as the same sort of gist as the derivative, but you can split these things up over intervals. So if you think of it as area going from a to b, then finding the area from a to c and then adding it to the area from c to b, whoops, should give you the same. So the area, finding the area from a to b should be the same as finding the area from a to c and then adding in the area from c to b. Okay, that's what they're getting at in this one. Okay. What else? You can read the other ones in the book, but I think they kind of go along the same lines of what we learned with antiderivatives. For example, for the integral from a to b of f of x plus or minus g of x dx, you can split that into 2 integrals and just find the area from a to b of f of x dx, and then plus or minus the integral of g of x dx from a to b. Things like that. We'll leave it for you, so go ahead and read the rest of those, and we'll see you next time. Okay, thanks, bye.